and welcome to the Science Hub. I'm your host, here to guide you through exciting learning experiences. Don't forget to like, subscribe, and share our content. And yes, also join our community on Facebook at the Science Hub for more updates and discussions. So yes, let's get right onto it. On our screen is a question on decay processes. We are looking at decay processes. So this question requires us to look at the disintegration energy as well as the kinetic energy. So it reads the RA 226 undergoes alpha decay according to RA 226 breaks down to give us Rn 222 and an alpha particle. So basically our problem is saying radium breaks down to form a daughter nuclei of radon and helium, which is our alpha particle. Calculate the Q value for this process. The part B of the question goes on to say, if the original radium nucleus was at rest, use the conservation laws of momentum and energy to find the kinetic energy of the alpha particle after the decay. After you've found the kinetic energy of the alpha particle, comment on the result that you get. So let's work on part A, where we're looking at the disintegration energy. The disintegration energy is the Q value. They want us to calculate the Q value of this alpha decay. So I pasted a formula there. Q is given by mx minus my minus m alpha. That symbol, we're going to use it as alpha. Pardon me, I couldn't find the alpha symbol on my keyboard. Times c squared. So we are going to say Q is equals to mx minus my minus m alpha times c squared. Mx is the mass of the parent nucleus. My is the mass of the daughter nucleus, and m alpha is the mass of the alpha nucleus. Let me write that there. Mx mass of the parent nucleus, my mass of the daughter nucleus, then m alpha is the mass of the alpha particle. So if you look at your periodic tables, or for accuracy, if you look at your data booklets, you'll find that the mass of radium is 226.025410. 226.025410. Then the mass of radon is 222.017578. Then the mass of the alpha particle from our data booklet is sorry about that, 4.002605. So those are the values that we're going to use. Then our c squared is given the value of c squared, yes, that's my squared there, is given the value of 931.494 mega electron volts per atomic mass unit. So those are our values, mx, my, m alpha, and our c squared. So we're not going to feed our data onto the equation. Q is equals to 226.025410 minus 222.017578 minus 4.002605, all multiplied by times 931.494. Oh, sorry, I put an 831 there. 931.494 MeV PAMU. So if you punch these numbers on your calculator, you will then, if you clear the brackets, oh sorry, the bracket is the symbol is AMU there. So this gives us Q is equals to 0.005 229 AMU times 931.494. You'll notice that if you punch these numbers as given on the question, the answer does not come out well. If you punch it as 226 minus 222, you get a 0, minus 4, you get a 0. So we need these long numbers for us to get the answer that we're looking for. So the Q value now is, from punching my calculator, I'm getting Q is equals to 4.870782126. I'm hoping that you got the same value. So if you check from your mathematics, the AMU and the AMU, they cancel out. So our answer remains in mega electron volts. So that is our Q value. If we bring it down to 3 significant figures, our Q value is now 4.87 mega electron volts. So that is it on our part A of the question. Now